This video covers section 1.1.2 of Griffiths E&M, talking about vector algebra in component form. Previous videos have talked about vector manipulations, but we didn't specify anything specific about each vector. We just said an abstract vector. Okay? But we are going to break down a vector into the different components that make up that vector. Right? We can make up any particular set of components we want, but we're going to choose to pick components that lie along particular axes that are important in our problem. So in this case, we'll talk about Cartesian coordinates. So we'll break down a vector into Cartesian components. So let's start with our Cartesian coordinate system. I will draw the x-axis like this, the y-axis like this. All right, and we need to put a z-axis somewhere. All right, the x-axis is coming out of the page, the y-axis is to the right, and we define the z-axis with our third spatial dimension using the right-handed rule. So we define everything within a right-handed coordinate system, which is why we use the right-hand rule to manipulate our vectors. Okay, so if I do x hat cross y hat, that's z hat, and that is pointed up. Oops. That's why we already orient our coordinate system like that. If you chose down, which is also perpendicular to the xy plane, you would be using a left-handed coordinate system, and every time you use the right-hand rule, you would get a negative sign off on all of your problems. All right, so if I have a Cartesian coordinate system, x hat, y hat, z hat, and I have some vector that exists in space, I can decompose that vector into the components that are in each of these Cartesian directions. So I can write my vector A as being AX, which is the amount that goes in the x hat direction, AY, which is the amount that goes in the y hat direction, and AZ, which is the amount that goes in the z hat direction. These are the different components. All right. So I can now manipulate this vector like I did previously, but looking at the components individually. All right. So I said previously that I can add two vectors, right? So let me go ahead and define some other vector. I will define it. I won't draw it, but it will be some amount in the x hat direction plus some amount in the y hat direction plus some amount in the z hat direction. I add those two vectors together, and I have to add each component separately. AX plus BX in the x hat plus AY plus BY in the y hat plus AZ BZ in the z hat direction. That's how you add two vectors component-wise. I can also multiply a vector by a scalar. All right, we defined that in previous videos. This scalar can be multiplied into each of these components. So here I'm just rewriting the definition for the vector A in component form. And now each component gets multiplied by that scalar. Now we talked about dot products. We can then take the dot product. Let's go ahead and take the dot product of a vector with itself. That is a dot a, and now instead of describing a dot a as the magnitude of a times the magnitude of a times the cosine of the angle between them, we're going to look at each component specifically. So we have this becomes a x squared plus a y squared plus a z squared. I'm multiplying the x component of each of these vectors and adding it to the y component of each of the vectors and adding it to the product of the z component of each vector. So another way we can write that is this is a squared, this is ax squared plus ay squared plus az squared. So the magnitude of our vector is the square root of all of the components squared and added together. This is essentially Pythagorean's theorem. All right, so we talked about one way to multiply vectors together by the dot product, and you know that there's another way. We can take the cross product. We can take the cross product of two vectors, and this is done by taking the determinant of the matrix, where I'm specifically writing each of the components and then taking that determinant, which I will not do, but I'll leave that for you to do.